Let us start this lecture with a thought process from Albert Einstein. Life is like riding a bicycle. To keep your balance, you must keep moving. Actually, this is very important, even though you may have some problems and then some success and failure, but one has to move on. So, in the last lecture, if you recall that we basically looked at how to analyze a two-dimensional diffusion flame, and we invoked the continuity equation, momentum equation, species equation, energy equation, all those things, right. In the last lecture, we basically derived a relationship involving the universal variable, in which you can express the fuel and oxidizer, because both for the fuel and oxidizer you can solve one equation, right. If you look at, we have basically looked at this expression, and which is YR is basically, it can be either fuel or it can be oxidizer, right. So, the equation form will be similar. Keep in mind that this is the partial PD, partial derivative partial differential equations, and now this is second order, right. We need to solve, we can also do little more simplification, take considering the assumption we have made, and this is basically we can convert into a diffusion equation, right, by considering y is equal to Byt, right. And if I want to look at basically dou y by YR by dou y, I can write down this as basically YR by dou t, and I can write down dou y by dou t, right. And this is term, if I take it that this is nothing but here what, basically By, right. If I use this one, and this is dy by dt is nothing but By. So, therefore, this will be basically dou, or I can say this is ordinary differential dy r by dt, because the function of t only, right now, and then V y. So, therefore, I can write down, that is basically dy by, I can write down this is, I can write down Vy dyr by dy is nothing but your dyr by dt. So, I can derive this expression. Keep in mind that these are basically a differential equation of second order, and it has to be solved, right. And this equation is known as the Bucs equation, right. This equation is known as, because the Bucs equation. He derived this thing, both the guys, so therefore, it is known as that, and we will have to now apply the boundary conditions and other thing. Keep in mind that this equation is valid where, all the region except on the flame surface, okay, right, and therefore, the source term has been neglected in both the equation. So, now if you look at inner wall exists at x is equal to 0, right, and outer wall at x is equal to L2, right. This is basically L1, okay, and L2. So, the initial and initial conditions and the boundary condition are given as a, initial condition will be t is equal to 0, right. T is equal to 0 means y is basically 0. YR will be what? YR will be whatever at the initial condition. In this case, this will be fuel, right. In this zone it is a fuel. So, that is equal to, you can say, is equal to y f, right, of at this point, right. And boundary condition x is equal to 0, right, at this point, right, this is x is 0, then gradient dy by r by dx at the 0 x is 0 in this point, this is 0, and that what it says, it is basically symmetric condition, right. Flame is symmetric, that means other half will be also there, right, you can see. And similarly L2 by at x is equal to L2 at this point, dy by r d 0, that means again it is gradient is 0 at the far away air side, you know, if you look at, there will be no gradient because your flame is here. So, it is far away from the flame. So, you can expect the gradient will be 0. Now, applying this boundary condition, we can obtain a closed series solutions, right, and that you can get in this form, that is yr divided by yr naught is equal to y f naught L1 by L2, right, and yr naught is coming over here because you are just dividing, right, and y ox naught divided by yr, and this nu is your stoichiometric ratio, right, and L2 minus L1 divided by L2, and this is your series solution. I would suggest that you can derive this because due to paucity of time I have not derived it, and this is a series solution you might have done in your you know, math course, right. This is n can be 1 to infinity thing, but however, when you compute you will have to do a certain number of these things so that it will be good enough to give you a result. You should not take 1 or 2, but at least something maybe 20, 30 kind of things. And keep in mind that this term is this is the zeta, I can say zeta is y pi square d 1 2 by nu L2 square. So, this expression you can write down as basically minus zeta n, right. This will be exponential terms, right. And keep in mind that we are interested to find out the flame locus, that is our objective, right. And once I get the flame locus, I can find out what is my flame length. So, keep in mind that this yr by yr naught at the initial conditions is the non-dimensional mass fraction of the reactant, right. If it can be both fuel, it can be both oxidizer, and yr naught is nothing but here yfo plus y oxidizer O divided by nu, that we have already seen, right, this thing. And at the locus of flame, at the flame surface, what will happen? Yf will be 0, right, and so also y oxidizer will be 0, right. That means Yf will be 0 at the flame surface, y oxidizer will be 0 because it will be consumed instantly, right, as soon as it will come in contact with that due to the first chemistry. This term will be 0 here, this term will be 0. So, therefore, this 0 at flame surface. So, you can find out this is basically in this equation, you can say this is 0, right, because yr is 0, right, and then at the surface, and this is of course the initial condition, yr will be 0. But if I want to say that, then like this is will be, I can write down yr will be yf plus y oxidizer into nu at the flame surface. So, therefore, this will be 0 and this is 0. So, this will be 0 at the flame surface. Now, if this is 0 in this equation, if I say this is let us say equation 1 I am taking for the time being, okay. So, this is 0, then what will happen? There is a basically one is the series term in the right hand side of equation 1, and this term, right, and this thing I can say is equal to basically is E, right. E means I can take out this, I can say this is Y oxidizer by Y r nu L2 minus L1 divided by L1 L2 minus Y f L1 divided by Y r in the initial condition L2 is equal to E is equal to what? 2 by pi and 1 to infinity 1 by n sin pi n L1 by L2 cos n pi x by L2 exponential zeta minus n, right, and that is itself is E, right, because if it is it will be having some finite value. Of course, in certain situation you may get it, this series part will be 0, but here it will be some finite value on the left hand side. So, this infinitesimal must have a constant value at the flame surface. At the flame surface it will be have some constant, it can be positive, it can be negative, right, but it will be having some finite value at the flame surface, right. Now, so the series solution, if you look at, it is basically depend on, if you look at x by L2, right, it is depend upon x by L2 and it is dependent on zeta, right, and it is dependent by L1 L2, right. These are the values on which this has to be dependent. I will write down that a little better. So, this series solution depends on L1 by L2. Why I am saying so? Because what happened, like if you look at E is equal to 2 by pi, right, 1 to infinity 1 by n sin n pi L1 L2 cos n pi x by L2 exponential zeta n, right. So, therefore, it will be dependent on L1 by L2, right, it will depend on x by L2 and depends on zeta. At the Burner rim, that means here, right, this is your Burner rim, right, at this point, right, the series constant, I can call this as a constant value, right, becomes a square wave, right, and for x when x varies from 0 to L1 here in this region, right, it will be zeta will be 0, right, and Y oxidizer will be what in this region, because the fuel, so naturally it will be 0, right, is not it, because here no fuel can penetrate into the fuel stream, sorry, no oxidizer will penetrate into the fuel stream, and x2 when x between 0 and L1, this is the fuel stream, right, this is your fuel stream, right. So, it will not really, oxidizer cannot penetrate, therefore, this oxidizer will be 0, okay, and YR is nothing but your fuel at the inlet. So, if that is the case, then now what will be E? If you look at, this is equal to, we have already seen, right, that is E is Y oxidizer by nu YR L2 minus L1 divided by L2 minus Y F oxidizer YR oxidizer L1 by L2, right. So, what is there if it is 0 to x lies between 0 to L1 in this region, right. So, what is happening, y(O(x) is 0, that means this term is 0, right. Okay. So, if that is 0, so what I will get, E is basically equal to minus L1 by L2 and yr naught is nothing but here, this portion is what, is nothing but here yf naught. So, this is cancel it out, are you getting, this yr naught is nothing but your yf. So, therefore, you will get this term, right. So, therefore, E is coming that way, right. Let us now look at the for between your oxidized side, the L2 is between L1 and L2, right. In this case, yf will be what, basically 0, yes or no. In the oxidized side there won't be any fuel, that is the assumption. That means as soon as fuel or the oxidizer will come in contact or it will reach the flame surface, it will just consumed, the mass fraction of the fuel and oxidizer on the surface of the flame will be 0, it cannot cross each other across the flame. So, therefore, whereas yr naught we know that yx by nu naught. So, if I look at that in this term particularly, if I look at in this region, right, and this is your oxidizer region, right, in this region I am considering in this surface. So, that will be yf will be 0, this term will be 0 and yr naught is nothing but your, in this place what I will be writing, I will be writing y oxidizer by nu. So, this will of this and this will cancel it out, this will cancel it out. So, what you will get is basically you will get E is equal to L1 L2 divided by L2, no sorry, and so by that you can really get very easily in terms of these dimensions and then E, evaluating E. So, if you look at when the fuel air ratio is stoichiometric, he becomes 0, right. If you look at the other terms and if it is E is 0, right, what you will get, if E this is equal to, if you look at this is equal to 0 for because for fuel air stoichiometric. So, this is equal to 0. So, if it is equal to 0, what I will write, I will write down this ox O by nu yr L2 minus L1 L2 minus is equal to yf by yr naught L1 by L2. So, if you look at this will cancel it out, this will cancel it out and you will get basically yf naught is equal to yox, right, nu that is L2 minus L1 divided by L1, right. So, this is the expression one can get and which is basically you are looking at how it will be the flame surface. You can solve these equations, right, using this various condition and you are basically working on this side, on the oxidized side, on the flame side. Then for a particular, because you will be knowing this L2, you will be knowing this L1, you will be knowing this nu and all these things, all those things you will be knowing, right. So, by using this series one can get a various points you will be getting at different radial directions you will see and then zeta will be changing like that x and that series solution has to be obtained, right, and then you will get a contour like that and this is the condition which is over ventilated, right, and there is a condition where it will be under ventilated. Under ventilated means basically when there is an excess fuel, right, what will happen, E becomes negative, right, E becomes negative and flame becomes under ventilated and for excess air E becomes positive and the flame becomes under ventilated. Once you calculate this thing you can find out what will be the flame height, because flame height will be in this case this is the region what you can say as a flame height HF, right. So, this is the region what you can get, and by this you can really find out flame length. But limitation of this model is that it is a very rudimentary, and it requires a mathematical this thing, and then thin flame approximation need not to be right, radiation is not taken care. However, it gives some experimental data train, but not exact value. And there are several people who have tried to modify it getting analytical solution, and that is a one what we will be discussing is basically the Roper later on modified this thing, added some terms, and which is quite elaborate, I will not be discussing. But however, this is about the 2D flame, but there will be some axisymmetric flame which generally we use. For that, if you want to do, you will have to get basically the similar equations, but it will be the again second order equation you will be getting using the same similar analysis, but you will have to use basically Bessel function instead of series solution, you will get that. So, if you want to see, it is given in the book of Principle of Combustion by K.K. Kuo, you can see that if you want to see, but I will not be covering in the lecture. I think with this we will stop over. In the next lecture, we will be discussing about the Roper's analysis basically and also some experimental result, and how to estimate the flame length or the flame height of a jet diffusion flame. Thank you very much.